So I had a stop in NSGA. The next algorithm is the so-called Niche Pareto genetic algorithm, MPAA. And this is also a very interesting algorithm. This guy is very funny, Jeffrey Horn. Jeffrey Horn was a PhD student of David Goldberg at the University of Illinois. He's a very smart guy. He's a mathematician. But he ended up in a very small university in Michigan, in a college, because he likes teaching and he doesn't do much research. He's still around from time to time. He shows up at some conferences. And one interesting thing about this algorithm is the only algorithm, the only multi-objective evolutionary algorithm in which apparently Goldberg got involved. But Goldberg really had nothing to do with the development of this algorithm, but Jeffrey included him because he was his advisor at that time. So he included Goldberg in the original paper of the MPAA. It was originally released in '93 as a technical report, but it was published in a conference in '94. So MPAA is a very simple algorithm, and it departs from a very intriguing, very interesting idea. In MPAA, you take a regular genetic algorithm using something we call binary tournament selection. In binary tournament selection, you randomly select two solutions from the population, you compare the two solutions in terms of fitness value, and whoever has better fitness wins the tournament. In this case, what they do is they take two solutions selected randomly, and they take a sample of the population, which is also randomly selected. This sample is normally about 10% of the size of the total population size. So you have 100 solutions, your sample has 10 solutions. Now you compare solution 1 to the sample in terms of Pareto dominance, and then you compare solution 2 with respect to the sample in the tournament. So there are only two possible outcomes. Either one of the two is non-dominated with respect to the sample and the other one is dominated, or there is a tie. Both are non-dominated or both are dominated by the sample. Obviously, if one of the two is non-dominated and the other is dominated, the non-dominated solution wins the tournament. So you select that one. If there is a tie, he applies fitness sharing. But now, Jeffrey Horn, he did his PhD on fitness sharing. So he uses a very sophisticated algorithm called equivalence class sharing, which is applied both in decision variable space and objective function space. And that's how the algorithm works. So why is this algorithm so interesting? Because Jeffrey Horn was able to show that you could do the same thing that MOGA does, but without comparing with respect to the whole population. That using only 10% was enough. Obviously, this classification has errors, but he was able to show experimentally that this error is affordable. If you think about this algorithm, if instead of using 10% of the population, you use the whole population, this is MOGA. So this is faster than MOGA because you are never comparing each solution against everybody else, only with 10%, a random sample. But this is enough, and this works. Of course, it's not as good as MOGA in terms of the quality of the solutions, but it's good enough, and this is the fastest algorithm from the first generation. So it's a very clever algorithm. So the few comparative studies from the mid and late 90s indicated that MPAA was better than NSGA, but it was, of course, not better than MOGA, because if you compare everybody, this is the best you can get. And the tournament size is a critical parameter in MPAA. Of course, if you use tournament size equal to the population size, MPAA will become MOGA. But using only 10, 15%, that was enough. So it was a very clever algorithm. MPAA was used by some people, was not that popular, but some people use this in feature selection, fault-tolerant design, and so on. I also asked Jeffrey Horn in the 90s the source code of MPAA, and he told me it's very easy, you can implement it. which is a nice way of saying, no, I won't give you my code. It's okay, you know, I implemented the thing. So when I was teaching for the first time in 2001, 2002, my multi-objective optimization course, I told this story to this guy I mentioned before, this guy who was a very good programmer, and he is also a bit of a hacker. So one day he came to me and he told me he had the code from Jeffrey Horn. And I said, did you email him to ask the code? He said, no, I didn't email him. So how did you get the code? I said, well, you know, I hacked his website. I said, what do you mean you hacked his website? Well, he was able to copy the whole, all the directories in his web page because he didn't have that protected. And in one of these directories, he had the code of MPAA. So yeah, not that I needed the algorithm anymore, but he managed to get his code without asking, which is interesting, right? He didn't have to ask. So there was an MPAA-II, because these algorithms, this happened like in the movies, you know, you had to have the second part, and in most cases, the second part was not as good as the first part. Few exceptions, NSGA-II is of course the main exception, but there were second parts, so MPAA had a second part that most people are not aware of. It was published in 2001, and it's not a very exciting algorithm, it's actually very simple, and it was used in a problem of designing a groundwater remediation systems. In MPAA-II, they still use the binary tournament selection, but they changed the fitness sharing scheme. In this case, the niche count is computed using individuals from the next generation. This is sort of an interesting idea as well. This is called continuously updated fitness sharing. It's kind of an interesting idea. And they removed the magic of MPAA-II because it's not doing the tournament with the samples, it's doing something very similar to MOGA. So this algorithm is much closer to MOGA. But nobody really used this algorithm because at that time in 2001, there were more powerful algorithms around, some elitist algorithms such as SPA developed by Sitzler. The niche count is how many solutions are in the same niche. In the morning, I show these circles. Yeah, it's counting how many are inside the circle.
So if the in the same case, if number of, for example, if 5 solutions are there, then how you told that in the morning that you will panelize, one can panelize that solution. What is the significance of panelizing?
You reduce fitness, so the probability of selecting the solution decreases. So the solution becomes bad because it has many other solutions inside the same niche. So whoever is alone has a higher probability of being selected. So he will win, will always have children. And the one who has many will have no children, so he will eventually die. So it's very simple.
Because all the solutions with diversity is less in the solution, there is no need to select the same type of solution. That's why we are doing this.
No, well, if you use fitness sharing by itself, this mechanism spreads solutions. So it works like magic because this penalty decreases the probability of selecting a solution, so it will work on its own. You don't have to do anything else. You just put the formula there and it will do its magic. It's very nice. We will get to this tomorrow, how fitness sharing works. But it's very simple. The only problem is the niche radius. This you have to figure out. It's not easy to do. So, okay. This was a non-elitist Pareto-based algorithm. So what is elitism? Because I mentioned in the morning, the last class in this first group is the so-called elitist Pareto-based multi-objective evolutionary algorithms. So what is elitism? In single objective optimization, when we use evolutionary algorithms, we call elitism to a mechanism in which the best solution in the population passes intact to the next generation. That means it's not affected by crossover or mutation. Normally, when you have a solution, no matter how good the solution is, this solution becomes apparent, so it's recombined with somebody else who is also a good solution. Two solutions generate two children, and the two children are mutated. That's how it works. So it could happen, however, that you have a really good solution, it recombines, and this also happens in life. You know, children are not as good as the parents. You know, you want them to be better. That's nature. They are supposed to be better. This doesn't always happen. Sometimes the fitness of the children is lower than the fitness of the parents. And this is recombination, you know. That's what is supposed to happen because you are changing components in the string. So to avoid this problem, you simply retain whoever is the best in the population, the highest fitness, this guy, you will copy exactly the same to the next generation. So this is very nice because if you do this, you keep monotonicity in the population. That means the fitness will never decrease, the maximum fitness will never decrease. Can only stay the same or improve. Of course, if it doesn't improve in a long time, in several generations, then probably you already reached the optimum, or at least the algorithm won't be able to find anything better. So it's possible to prove convergence of an evolutionary algorithm using this operator, elitism. That is a very important operator. Now, elitism in single objective optimization involves retaining one solution, only the one with the highest fitness. If you have 2, 3 solutions with the exact same fitness, then you can randomly select one of them and it's okay. But in multi-objective, which is the best solution? We don't have a notion of the best. We have non-dominant solutions. So in theory, all the non-dominant solutions should be retained. And this is a problem because the size of this set will grow very quickly. So in a few iterations, you may have hundreds or even thousands of non-dominant solutions. And this is a problem. So in the old days, the notion was, let's retain all the non-dominant solutions, put them somewhere. We call this the external archive, but it's not really an archive. This is a data structure, it's retained in memory, otherwise it will be too slow to access this information. We normally use an array, and we store non-dominant solutions in there. But because having too many solutions, if we compare these solutions with the main population, is too costly because we may have thousands, then normally we set a bound on the maximum number of solutions that we will retain. And we will see these algorithms that use elitism, they always use a bound. This is very important, particularly if elitism plays a role in the selection mechanism, like is the case of SPA. Not in every algorithm this is the case. In some algorithms, the elitist solutions are stored, but they are never compared with the main population. If that is the case, then you can have larger archives. But still, you don't want the archive to be too large because there are other issues. So there are two main forms of elitism. The first is through the use of an external archive, which is also called external or secondary population. This is a data structure that resides in main memory and which stores the non-dominant solutions that are generated during the evolutionary process. This is the most common. The second is using something we call plus selection. Plus selection was invented a long time ago in evolution strategies. In the genetic algorithm, you have a population of a size m, then m parents generate m solutions, and the new population replaces the previous population. It's always total replacement. So the children always replace the parents. However, in the plus selection, you have m parents, they generate m children, take the union, and you retain the best half. So if there is a parent that is better than one of the children, he will survive. He will be retained. So this selection is implicitly elitist because whoever is the best, he will survive, right? Because this guy will be better than his offspring. So this mechanism is used by NSGA-II. No other multi-objective evolutionary algorithm uses this. Most of the others use the external archive. And there are reasons for this. This mechanism has some weird theoretical problem. In practice, you may lose solutions. In some very specific cases, some solutions won't be retained using plus selection. But this is a complicated story, so I won't get into the details. In practice, it works most of the time. 99% of the time it works. Elitism is important because it's required to guarantee convergence of a multi-objective evolutionary algorithm to the true Pareto optimal set. This was proved by Gunther Rudolph and Alexandru Agapi in the year 2001. It's actually this, I put the wrong reference. Well, there is also an interesting story about this proof because they originally published a proof in 98, a proof of convergence, which is, however, wrong. And then nobody realized it was wrong. It was Gunther himself who realized there was something wrong in the proof. And they rewrote the thing, they fixed the error in the proof, and they published this again in 2001. This is Eckhard Sitzler. Eckhard Sitzler started this new family of algorithms called the elitist Pareto-based methods. In his PhD thesis from ETH Zurich in 1999, he proposed the strength Pareto evolutionary algorithm. And this is a very interesting algorithm. This is the first algorithm, I could say, really developed by a computer scientist who was interested in producing something elegant, something more powerful. And he got inspiration on several of the previously existing algorithms, like NSGA, MOGA, and so on. And this algorithm is also very famous because it was the first multi-objective evolutionary algorithm to be published in the IEEE Transactions on Evolutionary Computation, which, as I said before, started in 97. So NSGA was published in Evolutionary Computation, the other journal, in 94, but this was published in 99, and very soon it became a highly cited paper for one simple reason. Anybody who wanted to publish a new multi-objective evolutionary algorithm in the transactions, they had to compare with Sitzler. So everybody was citing this paper. And it's also a very good algorithm. The source code is available in the public domain. So SPA uses an external archive and generalize this notion of elitism by storing all non-dominant solutions obtained at each generation into this archive. The archive is used to compare or to select solutions. You compare the main population with the secondary population. So at each generation, the non-dominant solutions go to the archive, and as I said, the archive participates in the selection process. For each individual in the archive, they compute a value that they call the strength. The strength is really the same as the rank used by Fonseca. But Eckhard Sitzler didn't know how to call this, so he used the word strength. And this value is proportional to the number of solutions that a certain individual dominates. So that's how a strength is defined. Now, the fitness of each individual in SPA is computed based on the strengths of all the individuals in the external archive to which a certain individual dominates. So it's computed based on this measure. So this is similar to MOGA as well. But Sitzler realized that if the size of the archive was not bounded, if he allowed any number of solutions to be in the archive, very soon the selection pressure will go away because the number of non-dominant solutions started to grow very quickly. So he realized this is a problem. So to fix the problem, he decided to prune the archive using a clustering technique. He used a very old method called the average linking method. So he set a limit on the size of the archive, for example, 100 solutions or 200 solutions. And once he reached this limit, he applied this algorithm, and he had clusters of solutions. That means this is like fitness sharing. Imagine you have a circle around a group of solutions. And what clustering does is it estimates the center of the circle and tries to retain the solution closest to the center, and everybody else gets deleted. So if you have many clusters, these clusters are very small, so you will have the solutions distributed in a very homogeneous way. So it's a very nice idea, very simple, but these algorithms are order n squared as well. They are not very efficient. But this worked, this worked very nicely. So he did this each time the archive contained more than 100 or 200 solutions, the limit he set. So this algorithm was used by several people. Originally, Sisler himself was using this in computer architecture, some problems in computer architecture, but over the years it was used in medicine, it was used in civil engineering, in several domains. It became relatively popular over the years. There was an SPA-II. However, SPA-II is not a new algorithm. This is like an upgrade of Windows. You know, you get Windows, a version of Windows that is garbage, which is normally the case, and then they give you an upgrade, which is the same operating system, but this version works somehow. So they just call it something else, right? They say one is Vista and the other one is Windows 7. It's actually the same. It's just Vista doesn't work, Windows 7 works. So it's the same here. They only fix, the original SPA work, but they changed 3 things in SPA-II. So the fitness assignment is done differently. They call it a fine-grained fitness assignment strategy. So it measures dominance in the 2 directions. Not only how many solutions it dominates, but how many dominate this guy as well. So he measures this in the 2 directions. They changed the density estimator by a more efficient clustering algorithm. This was something I think somebody told Sisler in his PhD defense. And they changed the mechanism to truncate the external archive, because in the original algorithm, because of a mistake in the code, it will always lose the 2 extreme points of the Pareto form. This was because of an error in the code, so they fixed this. SPA-II was not as popular as SPA, but still some people use this in portfolio optimization, in finance, in a lot of engineering. Some people from ETH use this in genetic programming. So it has been around, and still some people still use these algorithms. Then we have NSGA-II. NSGA-II is also a very interesting algorithm. NSGA, as I said before, was not a very good algorithm. Was very inefficient. The results were not very good. But NSGA-II is a completely different story. Actually, this is not a small upgrade with respect to the original algorithm. It's completely different. The only similarity is the name, but everything else is different. So this algorithm was originally proposed in 2000 at a conference called PPSN. And then there was the journal paper published in 2002, which is a highly cited paper even today. It was the most highly cited paper in engineering for several years. So it's a very simple idea, actually. NSGA-II first, it does the non-dominant sorting, but in a very similar way as MOGA. Instead of removing solutions and resorting again, they do it in a single pass, which is, of course, the way to do it. This was actually very funny at that time, like in the year 2003, 2004. When NSGA-II started to become popular, they will make claims saying things like, this is a more efficient way of doing non-dominated sorting. And whenever they say that, I always told them, well, you know, this is the way everybody else was doing non-dominated sorting. The only guys who were doing non-dominated sorting in N to the third were you guys with the original NSGA. Nobody else was doing that. So you improved your own algorithm, but you didn't improve the other algorithms because everybody else was doing MOGA's non-dominated sorting. But yeah, okay, this was a big improvement. But the key element is not that. The key element of this algorithm is this operator. It's called the crowded comparison operator. Basically, what the NSGA-II does is to try to produce what we call a complete ordering. That means no ties. Okay, so it has a selection mechanism in which a solution is compared with respect to another one, first in terms of Pareto optimality. So if this solution dominates the other one, okay, it wins. That is clear. But if there is a tie, that means it doesn't dominate the solution, but the other one also doesn't dominate him. When there is a tie, this operator is used. Basically, this operator only requires to sort solutions with respect to one objective. Then we build, I don't think, I will put it in the practical session, but you have solutions sorted with respect to one objective, and you draw a rectangle around the solutions. So I sorted solutions, and I have this solution, and I go to the previous and the next, and I build a rectangle. So I compute the perimeter of this rectangle. And this is my crowding measure. So I do the same for the other guy, because remember I comparing this solution with respect to another one. In terms of Pareto dominance, there is a tie. You know, I don't dominate him, he doesn't dominate me. So I compute the two rectangles for the two solutions. Whoever has a bigger perimeter, that means this solution is farther away from its neighbors. So this is good, and this guy wins the tournament. So why is this good? Because if my neighbors, you know, the point after and the point before me are very close, and the rectangle is very small, that means that in this region of the Pareto front, there are already too many solutions. So I'm not interested in having more solutions there. But if this solution is really isolated, you know, my neighbors are very far from me, I need more solutions there. So I'm going to favor this solution. So it has a higher probability of being selected. So it's a very clever idea. It does the same as fitness sharing, but you don't require a parameter. You don't need the sigma share. This is wonderful. So if this is so wonderful, why is that this algorithm is not the state of the art anymore? Because this operator was really conceived only for two objectives. This notion cannot be generalized. If you want to go to higher dimensionality, 3, 4, 5, 10 objectives, you will have to replace this operator by a clustering algorithm. It is still possible to do it, but it's not going to be that efficient anymore because clustering requires parameters. So it was nice, but since the early days of NSGA-II, people realized that this approach had limitations. So it was a standard for a long time, more than 10 years. And the fact that the source code was released contributed to its popularity because people could actually use the code, and the code is very well documented, so it's very easy to use. And it became probably the most popular multi-objective evolutionary algorithm of all times. However, as I said, it has some limitations. For example, it doesn't work properly with more than 3 objectives, mainly because of the density estimator. If you replace the density estimator, then it will work. Also, in the old days, there was some experimental evidence indicating that NSGA-II works better with real numbers encoding as opposed to using binary encoding. Binary encoding is not that good because the operators of NSGA-II using real numbers encoding are very powerful. SVX, it's a crossover designed by Kalyan, and parameter-based mutation. Those two operators are very powerful in continuous search spaces. In binary encoding, he uses conventional crossover and mutation operators. They are not bad, but they are not better than the operators used by SPAA, for example. It has a similar performance. So it's a very, very interesting algorithm, very popular, many applications. This is a very, very tiny sample of the many applications that have been developed around this algorithm. It has been used in every domain you can possibly imagine. Lots of applications in engineering, but also in many other areas in general. Yes? I could not hear you very well.
In
If you can use it with more than 2, yeah, you can use it. The perimeter, yeah. Perimeter of the rectangle. But what Euclidean distance would you use? The diagonal of the rectangle?
Like if we are working on
Uh-huh.
that solution, so here if we use the Euclidean distance for I minus 1 and I plus 1 solution, then is it okay? Because we have parameters.
Well, but yeah, you can use whatever you want, but it's not necessary, right? Because the perimeter is very easy to compute in this case. Because if you think in 2 dimensions, you always have the coordinates of these points. So you can always, because you have the objective function values, right? Those are the coordinates. So getting the perimeter is straightforward. You are not gaining much if you change this by the Euclidean distance. Still, it won't scale. In clustering is different because in clustering, you are considering a circle around the points and you retain only the center of the cluster. And this you can scale to any number of dimensions. If you compute Euclidean distances without sorting the solutions, it could work, but then it will be the same as doing clustering. The k-neighbors algorithm is Euclidean distance. So that's probably what you meant. Yeah, you can do that, and this will work in any number of dimensions, but it's not as efficient, and you require a parameter. Sure.
Here only two, here in counting distance, we are working for only two solutions. And in clustering, more than 2 solutions is possible.
Yeah. But that's what I'm saying. In here, it's very easy to see how to measure distances because you only have 2 objectives. But imagine a problem that has 10 objectives. If you have 10 objectives, how do you compute that? How do you know how crowded is the region? Because at the end, you wanna know how close you are from your neighbors. So if you compute the Euclidean distance with respect to each of your neighbors in the 10 dimensions, then it probably won't make much sense, the information you will obtain, right? You will have a value, but at the end of the day, this value can have a very high variance because you may be very close in some dimensions, very far in other dimensions. So once you normalize, you get an average, for example, of this. The average may not make sense because the variance is too high. So this information you can use, but in most cases it's not very, very reliable. That's the problem. And this information you are using to break a tie, to know if one solution is better than another. So if it has a big bias, then the selection is not good. And the algorithm, of course, still works. It's not that the algorithm doesn't work. It's just the selection you are using is not very reliable. That's the problem with using Euclidean distances.
Actually, if I'm matching into high dimensional with the Euclidean method, then I find that to find the parameter of in high dimension is more difficult as compared to
It is, yeah, it's tricky. It's possible to do it, but most people don't like it for some reason. There is a version that uses that.
I asked because this is the solution what I came in with. It's just involved right now. So I asked because if I'm missing something that
No, you're not missing anything. It's just, it's normally a lot of trouble to do it. And the problem was in the old days when NSGA-II became famous, nobody paid attention to this. Because people said, okay, I have the code, I execute the algorithm, and it works. Of course it works. You know, it's an evolutionary algorithm. What did you expect? It will work. Is the solution okay? No, it's not okay. But it works. Crowding produces something. It will tell you this solution is better. Is this result reliable? Of course not. Because if you think of the operator, think about 3 dimensions, and you will see where is the rectangle. Because it's not using a hypervolume, it's using still the rectangle in 3, 4, 5, 6 dimensions. So you are only estimating distances in 1 dimension. What about the others? what if the dimension you chose for doing the sorting is not the proper one? So, and the whole notion of uniform distribution in high dimensionality is very tricky. So, most people didn't pay attention to this, and as I say, they say, well, the code works. Of course it works, because they never considered this as an exceptional case. Over the years, somebody developed a version of NSGA-II in which they replace this operator by a clustering algorithm, a very simple one, the K neighbors, which is Euclidean distances, sort of a brute force approach, and it works. This works with any number of dimensions, but nobody liked the algorithm. Nobody uses that algorithm because these algorithms are known to be very inefficient. So it takes a lot of time. If you go to a high dimensionality, it takes a lot of time to do all the computations. So that's the main limitation of NSGA-II. Yeah, when the perimeter is big, because the neighbors are very far.
So what if in current population there is not too much point in that rectangle? What if it implies that there is no Pareto solution? And
Okay.
we are populating again in that rectangle only. We are populating more points. But what if there is no Pareto point in that region?
Yeah, that may happen, but in here always the assumption is there will be solutions. And in continuous optimization, this is not a problem. Even if it's a discontinuity, it's fine. Because you will have to do this for everybody. So if there is nothing in there, no other solution, don't worry. The algorithm by itself won't be able to produce solutions in that region. Even it gets favor, but it won't get any children. So eventually, solutions will spread in the regions where you have portions of the Pareto flow. This is no problem at all. This you can control. Yeah, but it's a reasonable assumption that it may not work, but it works. That is not the problem. The problem is high dimensionality. It's really the only limitation. Okay, and the last algorithm, let's see, we still have a few minutes to see. Probably we will see this tomorrow because this requires some thinking, the data structure. In NSGA-II, another important detail is, and I will give you tomorrow the link where you can download the code. It's still available. There are several versions of NSGA-II. It's not only one. There are at least 4 or 5 different versions. The main algorithm was not improved. It's only the operators, the crossover and mutation operators. Actually, the first version that was released had some errors. And this thing drove us crazy for some time in my research group because at that time in 2002, 2003, people started to use the DTL set test problems. But the error the crossover operator had in the NSGA-II produced solutions that were beyond the boundaries of the decision variables. And it turns out that outside the boundaries, there was a better Pareto front. So it was impossible to defeat NSGA-II, just because this solution was not reachable. But it dominated the solution that everybody else was obtaining, because this was not attainable, of course. But it took us some time to figure this out. It was a very strange error, that the crossover produced solutions outside the boundaries of the decision variables. So you say the bound is between minus 15 and 15, and the thing will produce solutions in minus 20, in 25, completely outside the boundaries. And outside the boundaries, there was a better solution. So this was very odd. So the code is now heavily tested. I believe one of the test problems in the code, I think, has a mistake. But other than that, is very reliable code. And people have used this a lot. There are versions in MATLAB, in Java, in different programming languages, but the original one is in C. And it works both in Linux and in Windows. It's very, very good code. Okay, so I think we will stop here, and tomorrow we will continue with the other elitist Pareto-based algorithm.